Sarup received his PhD from University of Minnesota in 2019. And at EPRI, he's a technical leader within grid operations and planning group at EPRI Knoxville. He working on different aspects of the power system modeling, optimization, transmission planning, and operation, grid enhancing technologies, and transmission hosting capacity analysis. He has received Best Paper Award from IEEE Transaction on Power System and IEEE PES Prize Paper Award in 2021. He is also a co-author of a book, Electric Power Systems with Renewables, Simulation with PSSE, which is co-authored with Dr. Ned Mohan, and which talk about different aspects of the renewable energy. So today we are very fortunate to have him, and I'm sure we learn a lot from his talk. And with that, back to you, Swarup. Thank you for.
Thank you. Thank you for a great introduction. So yeah, say myself Swarup, and my today's agenda is to give you some information about grid enhancing technologies, what's happening in that space, why is it a hot topic right now, what are some of the challenges and potentially opportunities for students like PhDs, masters who are maybe still picking up your research topic. There could be some opportunities you can think about for selecting from this. For a quick assessment, so I get like a good idea of the audience. How many of you have like heard about this term grid enhancing technologies or never heard? Maybe one people who have heard, just raise your hands. I can just quickly see. Okay, I see few, so then it's good. I hope this session would be worth for everyone. And I have kept a background, so maybe let's jump into
Beautiful.
it.
Thanks,
All right.
David.
So as I mentioned, I want you guys to take away after this session. You should know what are the grid enhancing technologies, why is that become important right now, and then more importantly is where are some of those challenges, and every challenge is basically kind of a opportunity for you guys to solve that problem, right? So I want to highlight what are some of the challenges and key things which still needs addressing right now in the industry, especially for the utilities. So I want to take all of this understanding with you by end of this session. I won't go into details of each technology or much more granularity because this topic is so broad that you could perhaps talk for an entire day or two if you want to go into details, nitty-gritty. But I want to give you a high-level overview and just so you understand what each of this technology means and what are some of the basic fundamental understanding of what they are doing. Before jumping into the detail, I like to clarify this because I come from transmission operations and planning side. Now, when we talk about transmission planning, we think from a long-term perspective, right? So you are thinking about in the future, you will have this new AI is booming, you have new data centers which are booming, you have new renewable energy sources coming up across US or world. So you have all these new things, just as a population, as a user, your electricity demand is growing, and all those changes require some changes in your transmission infrastructure. And that comes from the planning. So as you think about 5 years from now, 10 years from now, and future, and see where I need to build new transmission lines, how can I increase my infrastructure to potentially be ready for the future situation. So that's the planning. And when we come into operations, that's your day-to-day or short-term evaluation and control. So every day, your system operators, you are getting electricity right now. It means someone in the system operator or operator room in the utility, they are controlling and making sure the system is reliable. So you have daily, hourly, every 15-minute evaluation. So that's day-to-day operation. They plan for next day. So that's what we call day ahead. So that's all operations. And now why I'm separating these two terms is some of these grid enhancing technologies, they are applicable for both of this, right? You plan for it from long-term planning perspective, and then you need to control some of these technologies in your day-to-day operations. So what happens is the problem and challenges based on whether you are thinking from planning perspective or you are thinking from operations perspective could change. So that's why I want to keep in mind that as you think from these different perspectives, your problems could be different. And so the way you should solve that, the solution you should come up with could end up being different. All right, so let's get into the core idea, what we want to discuss. GETS, or another short form for grid enhancing technologies. Now, there is no standard definition as such what technologies should be part of the GETS, but it's a common understanding now coming from FERC or NERC or other entities that these four technologies at least are being official, or I wouldn't say officially, but kind of a standard understanding among everyone that these four technology would fall under grid enhancing technologies. All that means, so what is GETS, right? What GETS is, how can we utilize your existing infrastructure, or how can we maximize the electricity that is being transferred in your system through the transmission lines in a quick and reliable and safe way. So you're looking for more faster solutions, but at the same time, you want to keep it safe and reliable. There are arguments and discussions going on for what additional technologies could be part of this, but that's a different topic I would not go into today. And there are some other different names that you may hear that are synonymously used with for the GET. So you might sometimes hear people call it alternative transmission technology, advanced transmission technology, or in short form ATTs. So when you do like a Google search, hey, give me what are GETs and what's some of the research going on there. There are tons of paper out there, and you will see this terminology being interchangeably used. So as I said, there's no official standardized definition, but it's a common understanding that these four technologies would be considered as part of GETs. And I'll go into each of this technology, what they mean and how they operate and why it makes a difference. So the second key important question is, right now you know what are GETs. They are for improving your transmission capacity or transmission system to utilize it in a better way and in a shorter time frame. Now, why? As I said, some of the features that people have shown a lot of results. You will see papers. They help for many different solving problems. So let's say your transmission system is congested. By congested, I mean there is no additional room for supplying transfer of power from one point A to point B. It's all already reaching its full capacity. Using some of this technology, there may be a possibility to increase that transfer capacity. So that's reducing congestion. The installation of these technologies are on a faster time scale compared to the traditional solution, which is building a new transmission line. So that takes many years and it's a slow process. Some of these technologies are also scalable, modular, portable. By portable, I mean you install this technology in one location. Let's say you have a problem in location A this year, and now you have solved it. now you have a problem in location B, and you don't need this device in location A anymore. You can relocate that device. So some of these technologies are portable. Then they help in a lot of other solving a lot of other power system problems and challenges. I have only listed few of this. So these are the features why this particularly these GETS technologies are getting highlighted and gaining interest now. So next key question, right? Now you know what are GETS, why are they being considered? The good important question one everyone asks is why now? Like some of these technologies have been there for many years, but why now? There could be several reasons, like maybe previously there was not enough knowledge or there was not enough incentives, but now things have been changing and in a very fast pace. For example, as I was started the talk, there's rapid growth in renewables. There has been rapid growth in AI. I believe a lot of you guys must be using ChatGPT or Claude or Gemini, some form of AI. All that means you need lot of more data centers, more processing power. So all this is growing. So your electricity generation and demand both are increasing at a rapid pace. What this means, your existing transmission infrastructure is pushed to its maximum capacity and it has reached its bottleneck where you need to expand your grid. Now, the traditional way, as I was mentioning, is to build a new transmission line, but that takes time and it's a slow process. It takes many years. Is there an interim or quick solution where something could help to alleviate this stress on the grid and then further squeeze some of the more capacity that may be available on the existing grid to basically make it more efficient and optimize the usage? And that's where this grid enhancing technologies come into play. So it's a near term, short, a quick solution. And very important to note, so I have put a star here. It's not a replacement. You would still need your traditional solution for stability and many other purposes. So you still need to build out new transmission lines, new transformers, and other things. But while that's being built out slowly, this could help you to bridge that gap and bring this new rapid growth online so that again everyone the need usage as a user we still have our lights on at, and not at the cost of reliability or safety. So that's what these gets are for, and all this being kind of now pushed forward. So there's a lot of policy and regulatory changes that's happening. There's a lot of incentives that's coming from various entities, not just in US, but across the globe in Europe and other countries as well. For example, there are these recent FERC orders, 881, 2023, 1920. A lot of this these are some orders which FERC is saying, hey, now all the utilities who fall under FERC jurisdiction, they need to comply with these policies. So there are so many DOE funding initiatives that being launched to support acceleration of these technologies. And even locally from the states, lot of public utility commissions and states, they are now mandating for utilities to consider these technologies when they think about planning and operations in the future. So that's why there has been a big push. Now you can see, and just to give you a quick small insight, right? For example, I've highlighted this snippet for this is from order 1920. It's this order is for the long-term transmission planning. As you can see, I've highlighted the transmission providers must consider dynamic line rating, advanced power flow control, advanced conductor and transmission switching, or in other words, topology optimization as part of the planning. So that's why this gets term and this is gaining popularity. Same with FERC Order 2023. This is coming from interconnection perspective. This is basically that where in the grid you can install a new load, or you can put a new data center or new renewable energy source. So how do you choose the best location? How do you minimize the cost of installation and all those things? And again, it asks to consider some of this, as I was saying, right? The term alternative transmission technologies. But more importantly, you'll see it also has some of this gets technologies like advanced power flow control, transmission switching among advanced conductors and others. So the key takeaway is that there is a new incentive and push across US and globally that these technologies should be considered and see how they can aid the traditional power system problem of expanding your grid, and see how you can leverage this technology for supporting those new renewable and AI and load growth. So that's the thing. And I love this slide. So you can imagine just for comparison, right, how big these FERC orders are. So as you can see, the 1920 is 1,300 pages, 2023 is 1,400 pages. So there's lot of things now utilities or industry needs to comply. And there's so all this means for you guys is there's a lot more opportunities and lot more research areas you can pick upon and tackle some of this real-time challenges which utilities are facing right now. So yeah, just okay. So now you know why gets, what are gets, and why now, right? So now let's understand briefly each of this technology, what they do and what they mean. So starting with transmission line ratings, right? So in transmission line, some of you might be, I don't know how many of you are involved in different types of studies. Some of you may be doing, let's say, steady state power flow analysis. Some of you may be doing dynamic analysis. Some of them you may be doing like a cost related, like production cost model or economic analysis or different type of studies or planning problems. In all those things, there is one key parameters you use as input data, which is your transmission line rating. Now, there are 4 different limits people as defined historically. The first and foremost is the static rating, which means that you find a rating for a line considering a worst case situation and or scenarios, and you use that rating for all of your studies. And the assumption or the understanding is that if you design your system considering this particular rating, no matter what happens, like it could be extreme wind or extreme weather, like cold, hot, whatever, your system would still be reliable because it was designed in such a way by considering the worst case condition. However, later people realize that, oh no, there might be different needs for based on different seasons. Excuse me, just drink a water. So they came up with seasonal adjusted rating. What this means is instead of using one rating for entire year, now you use different rating for different season. So your summer would be different, your winter would be different, your spring or fall. Some use 3 seasons, some use 4 seasons, depending on the entity, but you have now rating per season. And then now came people started thinking, why are we making assumption? Why don't we use the actual live weather measurement and calculate the rating based on current situation and not historical or assumption based? And that's where ambient adjusted rating came in, where people now start putting sensors. They measure the actual temperature near the transmission line location and then calculate the rating based on that. So your just temperature is varying. And then people were like, oh, why stop there? Why not measure all the other parameters as well? So that's what dynamic line rating is. So you will measure, there are sensors to measure wind, there are measures to solar, wind, temperature, many other parameters, and then calculate the rating. So that's what dynamic line rating is. What this means is now you are actually capturing what the situation is out there in the field and then saying that, oh, based on the current situation, I actually have maybe 100 megawatt more capacity compared to my static rating or seasonal rating that I have been considering. So does that allow me to push more power, more transfer capacity? Yes, no. That's where the challenge and discussions are ongoing. Should you fully utilize that DLR capacity? Should you push your system to that limit? Or should you limit your, there should be some wiggle room or headroom for flexibility for unexpected things. How much that percentage should be. So those are some of the questions people need to think about and address. Now, where the industry is, this is where the industry is right now. And it's slowly transitioning from left to right, where it's more dynamic. So you can see currently in planning, people use static rating. There are some who have transitioned to seasonal rating. Then in operations, people are currently seasonal, but they have started transitioning to ambient adjusted rating because that's what the FERC order 881 mandates. That order was, now there is no choice. Hey, you need to transition to ambient adjusted rating for operations. And then the most recent order, 1920, as I just showed in previous slides, is to consider dynamic line rating for the planning as well. Now, the most common response you will hear from anyone you will ask, you go to an industry and say, hey, are you considering DLR for your planning? They'll be like, no, no, no. It's not safe because there is so much variability, right? How can you predict from planning? You're looking for 5 years and 10 years from now. How can you predict what the weather would be? How can you predict what the temperature or wind or solar, any of those parameters would be in the future? You cannot design your system based on that because that poses a lot of threat and risk. Now, the question is whether you should completely ignore it, or maybe there is some middle ground where you can say, oh, maybe I should 20% of DLR, or add some cap or limit to it instead of utilizing or fully saying, oh, 1000 ampere DLR, maybe I can limit it to 700 amperes, something like that. So what would that value would be that will give you a more optimal result where your benefits outweigh the risk you are taking? So those are the questions which needs answers. You will do a literature survey on DLR in planning. You will not find much out there, or in fact, any paper. So again, these are some of the opportunities that are coming up where these question needs answers. So think about those things when after this session and beyond. So advanced conductor. So that was the dynamic line rating. Next, advanced conductor. Now, traditionally, the aluminum-based conductors, those are called the traditional conductors, whereas there are, which again, this list is briefly mentioned. The key is not these names, so don't worry about, oh, what's ACAR, triple AC, ACSR. That's not important here. And these are some of the advanced conductors which people are considering that could qualify as advanced. And now why they are advanced? All that means is these new types of conductors allow more current to flow from the line. What means that is your capacity of transferring the power through that transmission line for using an advanced conductor increases. That's what. So at the end goal, you see, right? Dynamic line rating, your capacity through the line is increasing. Advanced conductor, your capacity through the line is increasing. So the key takeaway from this thing is not the types of conductor. I mean, that's another research area that's going on where there is like a proper lab testing and stuff where people are testing each of this conductor type, how they will perform in extreme conditions, how they will behave, long-term stability and all that. That's from asset point of view. But from transmission operations and planning perspective, all that means is you have more capacity to transfer through the transmission line. So how would you pick which transmission lines you need to upgrade to advanced conductor, or should I use dynamic line rating? Which technology is more better under which situation? These are again the questions which people are still exploring. There are some papers out there exploring or showcasing studies which shows benefits of using this, but there is no systematic or mathematical approach right now you will find anywhere that says this is the strategy I should use, this is how I can pick which technology to use, this is how I can pick where this technology is applicable, this location or this site, things like that. So those are some of the questions which still needs answers. That was advanced conductor. So you are just changing the conductor material type. Now the third gets technology is advanced power flow control. Again, the power flow control itself, there have been many things historically and traditionally. You may have heard about phase shift transformers, phase angle regulators, series reactors. Those are some traditional way of having the power flow control. What is power flow control? It's the ability to change the way power is flowing through the grid. Transmission line, you have 90 amperes going on. You can put a PFC device and change that. You can say, I only want 50 megawatt to flow or 50 ampere to flow on this line. So the PFC device can help you to restrict like a flow gate or to increase. It can also push. I want not 90, but 120 amperes. So you can push in either direction. But the traditional ones include a lot of mechanical device like a transformer. It's a big size, the control of which is like takes time and not so easy. Whereas the more modern technologies, which they are being coined as advanced power flow control, they are power electronic based. So it's quick. So you just send a command and it will change. And it's scalable. As I was saying, some of those technologies, this is one of them. This is modular. So you can have like number of devices at the same location to achieve the full range of capability what you require. And it can relocate, so it's redeployable from one to other, supportable. So those are some of these features. To go just a one level depth of what this technically means, this APFC is nothing but a FACTS device, flexible AC transmission device. And within that, it's called static synchronous series compensator device, triple SC. So you will hear this term a lot if you Google search modular triple SC for APFC. All it's doing is it is injecting a series voltage on the line in perpendicular to the line current. In simplified terms, all it's doing is that it's dynamically changing the apparent or the line impedance. So if you increase the impedance of the line, you are saying, okay, I'm resisting, so less power will flow through it. If you are reducing, I'm allowing it to have more power flowing through that line. So bottom line, what this APFC is doing, it's allowing you to push or pull power on a particular transmission line wherever it's installed. So that's the key takeaway. So this APFC device is allowing that flexibility and control. What this means, if there is a transmission line which is, let's say, reached its maximum capacity, and there is another transmission line which is, let's say, 50% utilized. So you can install a device, this device on either of this line, and push the power away to the other line so they are kind of equally utilized, and that will allow you to have more transfer capability. So it's basically better utilizing your grid in a more efficient way. So that's what advanced power flow control is. And finally, the last piece, topology optimization. So in a simplified terms, for example, you have a two transmission line, right? And one of them have the rating, which limit of 50 megawatt, and the other one capacity is 500, but the flow is 60 and 400. So this line is right now overloaded. So if I switch off this line or take this line out of service, the entire flow is through the other line and it is still within the limit. Now, this is a very naive, simplest example, but the grid is complex, right? You have a whole mesh network. So now imagine that problem formulation. You have a lot of integer variable decision making where you have so many transmission lines to consider, which can be turned off, which can be turned on, such that these overloads or these problems in the grid will go away. So what's the best configuration of your network topology or network grid that will help resolve this problem? Again, this is from operations point of view itself is very challenging problem, because you can look from just this overload perspective and say, hey, switch off this line or take this line out, your problem is solved thermally. But you need to also think about your dynamic problems, stability problems, and your grid strength and other things. So there are so many other aspects one would need to consider. And that's why this particular, I would say, technology or approach is not so favorable among operators right now, but it's changing. So there are people working on developing some tools to better come up with decisions that are more safe. And now, if you think this from planning, it's even more challenging. Again, from those uncertainty perspective, how the future would look like, things would look like, how would you make decision now, design your grid by considering that. So think again, I'm trying to give you guys different areas where there are some ongoing challenges and which needs answers, and utilities are asking us questions like, what does this mean, or how can we make this decision? So think about that as you go through this information after this session as well. If you are researching, think all those questions from that perspective. So those are the four different technologies. So to summarize all that, as I was saying, the advanced conductor is quite well established. There is some research going on from the asset and testing point of view, from the hardware perspective, but not much looking from the mathematical problem or a research perspective. But in terms of DLR and PFC and topology optimization, as you see all this yellow and red exclamation, that's a lot of areas where there is still needs a lot of answers. And we have divided into different categories, right? Like I was mentioning, where this each of this tech. The first question is, which of this technology would be applicable for which problem, which location? Once you determine which technology, now how would you model these technologies in your problem formulation? So how would you model this technology in your problem formulation? Coming to operations, how would you control these technologies? Like take PFC, for example. You are installing a power flow device at 10 different locations. Now, how would a system operator make decision to control these devices? Right now, currently, the industry has, like you might be solving generator dispatch problem or a unit commitment problem or automatic generation control, AGC problem, right? So that's for the generators. But now if you add this device as well in the toolkit of the operators that, hey, you can control this as well, what would be those economic models? What would be those economic cost? Now, how those generator dispatch would change because of this control. So those are again some of the questions which people are still researching on and reviewing or looking to solve that. What would be the scheme or control scheme one should come up with? Centralized, decentralized, or a hybrid or things like that. So those are some of the things. How would it would impact protection, your grid protection? Again, a lot of questions. Then the acquisition and maintenance is from the asset perspective. So that's more on the hardware side. Like this PFC technology itself, what they do is, for example, in EPRI, we have set up a research hardware lab where they put this device through extreme heat, temperature, test it out, material degradation, aging of the equipment, and all those stuff. So, but that's from asset perspective. That's again ongoing research because it's a new technology. We don't have much of historical information like what's the life cycle, how frequently the maintenance is required, and so on. And finally, another most important is markets. So when you are doing, maybe some of you guys are working on market related research, when these technologies will enter the markets area, how would markets be impacted? Like what would be the, for example, in the recent general meeting, right? The power energy general meeting, in a panel session, I asked this question to them, right? Let's say you have congestion going on because of which your electricity prices have shot up. But if you consider either PFC control or dynamic line rating, you realize that there is actually more room and it's not actually a congestion. Would you stop charging your customers or change your the way you are doing the analysis? I didn't receive any response. Everyone was laughing because that's again an ongoing challenge. No one knows answer about. Right now, it's not. Right now, these technologies are not part of markets, but it will enter soon because of these FERC orders and everything. So those are again the challenges which are forthcoming and needs some addressing. So since we are limited on time, I that's why I focused on just the two technologies, DLR and PFC. And I kind of shared already a lot of this point in the previous slide, but just to summarize, right? For the dynamic line rating perspective, as I was saying, when you consider for long-term planning in the future, 5 years from now, 10 years from now, what rating would you use? Because dynamic line rating, it's changing dynamically every hour. But from 5 years from now, what is that? Which rating would you use? You would use the maximum rating which you have seen historically, or you would use minimum rating or something in between? That's the question which needs answer. And how would this, considering this rating, affect each of the study you have been already doing? People do a lot of different studies in planning, but now if you include dynamic line rating in there, your results will change. So how would you model or consider those and impact of those? So that's again something you should think about. Same with advanced power flow control. There are tools needed. There is the modeling research going on. Some software vendors have started including this, like Power Factory has released their newer version, which includes support for APFC. PSSC, like Siemens, they just started it, but there are still, it's a question. There is no standard right now. So what would that standard specifications look like? That this should be how the device should be performing. You guys do it all the time for IBR and studies, right? You guys are looking for how the IBR should be performing. What are some of the performance criteria? Especially, there are standards coming up like 2800, so on. But there's nothing like that for these GETS technologies right now. So that's something to think about. So how you would integrate into those planning, operation, and so on. Markets, again, all these are the questions you should think about for each of this technology. Now it gets even more complicated when you want to combine multiple of these technologies. So considering one itself is a challenge, but now if you want to evaluate combined benefits, that's more even challenging. So again, think on those aspects as you think about research challenges which are needed right now in the industry. That's something that's going on. And just, I guess, I think this is my last slide. So we are doing, of course, some of the research to address some of these roadblocks, but obviously not everything, right? We do have our limitation of number of resources and people working on it. So we are working on some of these things like developing a reference guide or some software tools, but there is still a lot of questions and pending answers that everyone is looking for. So there's still a lot of scope, and it's just picking up this topic. So there's a lot more coming in and a lot more challenges one needs to solve before gets are fully implemented and accelerated across globally. So yeah, that's what I had. I think I kind of mentioned all the conclusions and future directions as part of through my slides. I would leave it now for questions. Thank you, guys.
Hey, thank you very much. Okay, so maybe first let's go by people online. So, any questions from the online audience? No question. Okay, we can get back to you if you have questions. So in the room, anybody?
Thank you very much for this nice presentation. I'm particularly interested in this topic of advanced power flow controllers.
Sure.
So I was wondering if, like, those are very nice questions all about whether what kind of control it should have, whether it should be centralized or decentralized, or whether transmission system operator controls it, or how it should be happen. So can we draw, like, first, what are the existing practices for facts in the system? Because we might already have these fact devices at not that scale, but at some scale we might have. Second, can we draw some parallels from HVDC, which also serves as a control device, which can reroute the power in the network?
Sure. Yeah. Definitely, we can. I'll address some of these points. So first, from the APFC or facts device perspective, actually, on the contrary, there are very limited facts devices across the system as we were looking through or interacting with different utilities and members. There are very few systems where some facts device exist, and let alone being controlled dynamically, because again some of these technologies have like mechanical installations and challenges to frequently change. So it's not a to go decision for system operator to change until there is some extreme case where they need to change something. So to answer your question, there are very limited devices, so there's no scheme right now as would be, let's say, SPP footprint. Just giving an example. But when you install this APFC device, it won't be two, because this device comes in a modular form. So it will be a lot of modules and lot of things to control. Some of the studies we have done, we came up with like, install this device in these locations and you need three devices or three modules at this location, 10 modules at this location, 6 modules at this location. So now you have around 20 modules to control. So the number of or quantifying the control number is more higher in APFC than traditional facts. And there are some, like we have, in fact, there's an open source, not open source, we have published openly to publicly available a paper which we have done with in coordination with Idaho National Lab. You can just search advanced power flow control Idaho National Lab and EPRI collab. There is a white paper, but it introduces some of those things, like what kind of control technique people can think about, different control options and so on. You will see, but that's mainly theory. No one has actually developed any mathematical model to design that solution, and let alone doing a study or showcasing the benefits of different control. So there's a ongoing research, a lot more to be done. The second question you asked about the parallel with HVDC. Yes, I mean, I would say it's similar. Even with HVDC, it's not that frequently controlled. And then on top of it, it's the same thing, right? You don't have that many HVDC lines. It's growing now. It's again gaining popular where HVDC line being considered. But there's also another thing gaining, like 765 kV lines is getting popular now instead of HVDC. But same thing, it's limited number of HVDC controls, so not that of a challenging problem when you think about the amount of devices you need to control here for EPFC. Does that answer your question? Yeah.
Indeed. Thank you. Yeah.
I had a question about incorporating the dynamic line ratings in long-term planning, and just sort of how that would work in practice. From what I can tell from what you described, that involves a lot of weather prediction combined with the effects that those weather conditions would have on the lines, and then extrapolating that out further. How does something like that differ from simple seasonal line ratings? Don't you still have to say, okay, here's the worst case scenario that we're willing to predict under these conditions?
No, that's a great question. And so the idea behind it is, right now, as you said, if you ask anyone, you will be like, no, we don't want to consider. But there is no mathematical I would say background or demonstration that why no. Now the way we have considered, or one could consider DLR for planning is, yes, there is a lot of variability and stuff. So think of it this perspective. Let's call 0% DLR is basically your seasonal rating, right? You are not having any dynamic, so you're going with static or seasonal. 0% DLR. And then you have 100% DLR, which is the maximum rating of any one of the line could achieve based on historical weather or prediction or whatever. Because you can have two different kinds of approach. One is you just make use of historical weather data. You have last 20 years of data and perform some statistical analysis, probability, and come up with that, hey, this could be a potential value. Or you can do a future prediction type of thing where you are predicting your weather forecast and so on, and then saying this could be a potential prediction of the rating. So you can obtain rating from two different perspectives. But now instead of using that 100, the rating you calculated, maybe you put some value or cap on that. You can say, what if I use not the entire rating which I calculated, but 80% of that value? Or maybe you can say, so what I'm trying to say is there is 0% DLR, which is your static, and then there is the maximum. There is a whole range of spectrum in between which no one is looking into. So maybe if you consider 10% increment or 10% increase from your static rating, or 90%, or putting a 10% cap of your DLR value, the risk with that is lesser than the benefits you are getting. So maybe this 10% DLR you are considering is saving you millions in line investment at the risk of maybe 3 million. So the question is there an optimal sub point in between which balances out or outweighs the benefits outweigh the risk? For some situation, the answer could be still zero. There could be a system, you do all this analysis and say, oh, looks like even if I consider 1% DLR, I'm at a problem. I have no benefits. So I would still go with seasonal rating. That's absolutely fine. We are not forcing here for anyone to use the DLR. We are saying that this is a systematic way one could consider DLR. And now you have a mathematical kind of showcasing, proofing behind your decision that, hey, this is why I made my decision. That's all what I'm trying to convey. You don't need to enforce anyone, but the idea is to explore that spectrum of 0 to 100% rather than just looking at the edge cases and saying yes or no. Does that help?
Yeah, that makes a lot of sense. Thank you.
Sure. I see a question in the chat. It's since SmartWire can adjust line impedance, how much they actually increase it? Like, can they decrease the impedance by around 50%? Thank you for the question. Yes and no. And I mean, yes, in the sense there are the transmission line where you can increase maybe even 100%, like twice, but it depends on a lot of other factors as well. Sometimes there is a limitation from voltage stability point of view, but from the device itself, yeah, it supports a big range of increase and decrease. So all you do is you keep adding more modules, the more capacity you need. But that's just from capacity point of view. But then if you start thinking from other perspectives like stability and stuff, it might be much lower.
One question. Are you sure? Okay, so once again, thank you very much, Swaroop. So sorry for that one.
Oh,
So
no.
we really appreciate. So that was very informative talk. So with that, so maybe round of applause.
Yeah, thank you very much. And I have shared the presentation. So yeah, feel free to look at, and my email ID is on the first slide. Feel free to reach out if you have more questions or if you're interested in any other detailed discussion of any particular topic. I barely scratched the surface of GETS, and I did not show, but in the slides, there is a last slide where I've thrown in some additional links. If you like to learn more about what happening around GETS, there are a couple of websites, EPRI and non-EPRI and other websites where you can look in more details of what's going in this space. So yeah, feel free to check out and explore and reach out anytime. I'm available.
Yeah, if you share the slide, that would be nice. Darling will put on the website too. So the link that shows up your talk. So always she can put the link to your slides as well.
Great. Yeah, I've shared with her already.
Oh, you did that? Oh, perfect.
Yes, yeah.
So then we have, thank you. Thank you very much. Okay. Thank you.
Thank
Have
you,
a great
guys.
day. See you sometime
Thank
soon.
you.
Okay?
Thank you.
Bye.
Yeah,
Bye.
bye.
Bye.